Hi, and Assalamualaikum warahmatullahi wabarakatuh. Welcome to week 9 of our video lecture. And in this week 9, we are going to look at basically the last part of discussion on BJT amplifier. So in this week, we are going to discuss about the what we call as small signal amplifier. What does it mean and what is its problem that lead us to be needing a small signal amplifier, I mean small input AC voltage. And then we will discuss about the equivalent model of an amplifier, which also include therefore the equivalent model for transistor. Let's begin. Therefore, acknowledging that there is this problem of distortion, we have to define what we call as small signal operation. So that's what we know as small signal operation. So what is small signal operation? Small signal operation is to have a small AC input signal. The emitter current has a DC component, we know, and an AC component. So if we try to write it out in mathematical equation, IE, the output current, the emitter current that is due to the VBE is built up or is composed of two parts: IEQ, which is IEQ, which is the DC emitter current. So the DC emitter current, of course, it comes from the fact that there is a VBB, the DC VBB, and we have a IE. So IE is basically the AC emitter current, which is coupled to the DC current. Okay, so as we can see, basically when we write in capital letter, it means it is in DC. If we write in lowercase, it means it is in AC. So there is these two component, right? So in order to minimize it, we know that IEQ, there's no problem with the DC component because DC component determine the Q point and it will not move because it is DC. The one that we want to reduce is basically the AC part, which is induced by this IE over here. So to minimize the distortion, we define a small signal operation as what? As basically we need to have a peak-to-peak current of the AC input that is smaller than that is 10 times smaller than the DC current. Okay, let me explain. So we know just now that we have this point Q that is defined by the DC component, right? And then we have the AC component. A small signal is operation is basically conditioned by if we have the peak-to-peak current. So this value over here, this range need to be smaller, 10 times smaller than the value of this DC current. Okay, then the value of this DC current. So if you measure, for example, if you read the value of this voltage, I'm sorry, not current, DC voltage. If you measure the value of this DC voltage, right, this range of this voltage need to be 10 times smaller than this value over here. Okay, so that is the definition of small signal operation. So in order to have a BJT amplifier that does not have too much distortion, we need to obey this small signal condition. The peak-to-peak current need to be 10 times smaller than the DC component. So what does it mean is basically if we have an example here, if in terms of current, so it is in terms of current, I'm sorry, not in terms of voltage. If we look at the current, if we have a DC component of current at 10 milliamps, then the variation of the AC current need to be less than 1 milliamp peak to peak. Okay, it is 10 times smaller than 10 milliamps, therefore 1 milliamps peak to peak. So the AC current, the range of the AC current peak to peak needs to be 10 times smaller than the DC component. So that's what we call as small signal operation. That is the first thing that we need to define, that we need to basically verify in our amplifier to make sure that we don't have a lot of distortion in the amplification process. So here we have an exercise. So we know the condition, peak-to-peak current smaller than 10 times than the DC component. So for example, if we have our circuit over here and it's given with certain parameters, if you were asked to find the maximum small signal emitter current, what you need to do is first to find the point Q, of course, right? To find the point Q. So in order to find the IEQ, of course, we know that IEQ is, what is IEQ? IEQ is the current that goes through the emitter, IE divided by RE, right? IE divided by RE. And what is IE? So if you want to find IE, IE is basically VEE minus VBE, right? Is VEE. VEE is voltage at this point, and VBE is the voltage in between B and E. Okay, that is actually obtained from this loop over here. You have minus 0.7 here, minus 2 volts, and RE. So by doing the calculation, we have the current emitter at point Q equals to 1.3 milliamps. Now that you have the current emitter, so the next thing is just to apply the small signal condition. So it needs to be, the peak-to-peak AC current needs to be 10 times smaller. Therefore, if it is 10 times smaller, then you'll get 130 microamps peak to peak. After understanding the concept of small signal and the condition of the input voltage AC that we can supply to the BJT amplifier so that it is not going to have a large distortion. The next thing that we need to also be aware of is basically the AC current gain, or the beta value that we called before. There is also a certain modification on it due to the utilization of AC input signal. So in all previous question, beta that we looked in that data sheet was the beta that given for DC current gate. So it was defined as the ratio of collector current divided by base current. But just like in emitter current, if we we know that we have another curve of IC versus IB, which is basically the slope of the graph in this graph would give us the gain of the BJT beta. So if we look at it, the curve is also not linear, and it depends. Remember, the beta depends on the operating point. What is the value of IB that you have, right? So if IB changes, then Q will change. Therefore, the beta will also change. Okay, the ratio between IC and IB, which is beta, will also change. The gain therefore may change as the AC current vary. So if you have a too large signal, then the amplification would be different depending on the position of the point Q. So in the data sheet, however, in the data sheet, this is usually given. However, if you were obeying the small signal condition, then the difference won't be too much. The gain are usually between AC and DC input voltage are pretty close. So for DC gain, some don't even give the gain in AC because they are very close if you use it properly. But some data sheet may give the difference gain depending on whether you're using AC or DC. So how do you find it in data sheet? So remember last time when we talk about data sheet, the gain is usually noted as HFE. So when it is in a capital letter, it means it's for DC. But you may also find a notation of HFE in lowercase. So if you find this, then this is basically the gain in AC. So there is a condition to be of the probably the peak-to-peak value that gives you this gain in AC. But if you don't have this, you might as well use the DC gain, because usually they are not very different from each other. Okay, so having understood all the potential problem of using basically the amplifier and the condition that we have set, therefore is what we call a small signal, we can now try to analyze our amplifier. But to analyze our AC amplifier, of course, analyzing a circuits mean you have to analyze all the characteristic of like voltage and currents in the circuit. So what we need to do is basically to instead of just in the circuit drawing a transistor BJT as just a BJT, we need to reduce, or we may want to model the transistor into a more simple component that reflects its behavior electrically. Okay, so here what we are going to do is basically to understand the model of the transistor itself. So just now we look at the problem related to amplification. Now we are going to model the amplifier, but before we model the complete amplifier, what we need to do is we need to look at the modeling of the transistor alone. After we've we've understood the modeling of the transistor, then we'll go to the modeling of the amplifier. So now is on the model of the transistor. There are two types of model. The first one is what we call as T model. So what is T model? The T model is basically, you know, transistor is in this form. You have base current. When you have enough base current, you create a current that flows through the collector and emitter. It can be modeled as such over here, where it is the form is similar to the letter T, so that's why we call as T letter, a T model. So what is the component of the T model? In the T model, we say that the emitter, so emitter is over here, right? We model the emitter diode of a transistor to act like an AC resistance. Okay, so we consider that in emitter we have a certain AC resistor. So the AC resistor is called R prime E, and in order to find that value of R prime E, is very easy. There is a specific formula for it. So this is the formula, is 25 millivolts. So this 25 millivolts come from basically a certain calculus. So we just gonna take the value to do our calculation divided by the emitter current. Of course, the emitter current need to be calculated like what we have done in previous slide. Once you have IE, because IE is part of the operating point definition of the BJT, then if you do this calculation, you will get basically what we call as the AC resistance of the transistor. So in other reference, you may also find before go to that, that is for emitter, and then for collector, the collector diode. So in BJT we have two diode, right? PN junction in emitter, PN junction in collector. So in collector, now the diode acts like a current source. So it is simply represented as current source IC over here. And what do we have? What do we have others? Others is that in other reference, you might find a reference that quantify this IC as the product of GM, a certain gain, multiplied by a certain voltage VT. So what is VT? VT is basically GM could be given, and VT is an equivalent voltage across the base resistor. So imagine if the base over here, you have a certain resistor at the base. The voltage across that base resistor in the base input is what we call as VT. VT as in the voltage for the T model of the transistor. So IC current over here, the current that is pulled by the collector, current source over here, will be proportional to the voltage across the base resistor. If you have a resistor, of course, here you might have a resistor. If you have a certain resistor, then it's proportional to that voltage across that resistor. Okay, and that is a certain gain of GM. At low frequency, the base emitter voltage can be written, of course, using Ohm law as VBE. So we know that there is still the VBE over here in T model. If you want to write the VBE, it's just Ohm law current multiplied by resistor. So the current is IE, right? Current is IE, and we know IE is very close to IC, which is this formula over here, multiplied by R prime E. R prime E, what is? It is basically what we call just now as the AC resistance of the transistor. And then we have a second type of model, which we call as pi model. So what is the difference with the pi model? So in pi model, in comparison to T model, what it does is it views the transistor as to create an equivalent impedance or equivalent resistor for the whole transistor instead of just the emitter. So for example, if we look at the T model just now for the BJT, for the transistor, we create an equivalent resistor just for the emitter. But here what's going to happen is we are going to create an impedance equivalent when we look at the transistor as a whole. So we view, for example, from this point, from the base, we're going to deduce the whole equivalent resistor for the whole BJT. So we also know that from previously that the base emitter voltage can be written as in the T model as VBE equals to IE R prime E. So the input base impedance therefore can be written is, if we look from this point of view, as a VBE divided by IB, the base current, right? So knowing that VBE just now, as we mentioned here, so we can write the input impedance of view from the point of view of the base as IE R prime E over IB. Okay, so this IE over IB, if we remember that IE in a BJT is more or less equivalent to IC, therefore we can write as IC over IB, and we know what is IC over IB. IC over IB is basically the gain of our BJT or our transistor. Therefore, the resistor from the point of view or from the base, it can be written as the gain multiplied by the resistor equivalent of the emitter R prime E that we have deduced in the T model just now. Okay, so instead of having a model that looks like this, a T model, it can be transformed into a model that now like this, which we call the pi model. Why the pi model? Because it looks somehow like the symbol pi. So instead of having the resistor at the emitter R prime E, now we include it at the base that represent the whole impedance of the BJT, and it is equal to beta R prime E, beta R prime E, right? And then we know just now that we have the voltage across the resistor at the base is the voltage we call just now VT, but now instead of VT, it's now V pi, is the voltage of the across the base resistor of a pi model. So that's what a pi model is. And then we still have on the collector part the collector current, but now the collector current is of course equals to Gm again multiplied by V pi. V pi is the voltage across the resistor at the base. So it shows that it shows somehow that the collector current is proportional to the voltage across the base resistor. So in other annotation, the B R prime E, because R prime E is coming from the T model, sometimes we can replace the whole thing as R pi. So R pi is the resistor, equivalent resistor for the BJT model in pi model. This is very frequently used as R pi. Instead of writing as B R prime E, we write it as R pi. So the voltage across it is called as V pi. So now in order to analyze, once we have that, what we can do is we can once we have a model, we can do analysis of the BJT, right? So we have, what we have to do is that once we have a circuit, for example, like this of an amplifier, to analyze it, to make the analysis simpler, simplify the analysis, we convert it into an equivalent model. So for example, over here, it's a pi model, right? It's a pi model. What is the difference with the pi model that we have seen, that we have shown in previous slide? It's just that just now the V pi, this branch and this branch are connected and both going to IE, emitter current, going to emitter current. But now we can see that the IE, the emitter terminal over here is going to the ground, so both of them goes to the ground. So it's the same model that we had just now. It's just now that it shows the model, the transistor model has been applied to the amplifier, where the emitter terminal is connected to the ground. So to do the analysis of an amplifier, just like any circuit analysis, if we have multiple source, which is the case over here, right? We have the AC source of the V input that we want to amplify, and then we have the DC components of VCC that will become here the DC voltage at the base, and the DC voltage that is also connected to the collector loop. So if we have multiple sources, you remember in basic electrical principle courses, what you need to do is to do use superposition theorem to separate DC and AC sources, calculate them separately, and then later you can add together the results. Okay, so I'm not going into the details of that. So the first thing is, of course, to do DC analysis. DC analysis means we are going to take into account the DC input, but we are going to neglect the AC input. So what we do is, if we are in DC, then all capacitors are open, right? All capacitors are open, because in DC the capacitor act as basically an open switch where no current, DC current, can pass through it. And then in terms of voltage supply, of course, if we are in DC, the voltage supply are shorted. It means it's just like it is connected through it directly, just like as if it is a conductor. And in AC analysis, what we do is the capacitor is going to be shorted because capacitor is act just like a conductor if we are in AC, and DC sources, the DC sources like the VCC will become, as we mentioned earlier, it will become what we call as AC grounding, right? So it absorbs all AC to leave just DC component. So here what we're going to do is we're going to study the AC analysis of the base bias amplifier. AC analysis of the base bias amplifier. So this is a base bias amplifier, right? So we have VCC, we have RB. So this is base bias BJT. It is an amplifier. We have V input, of which is the AC. So this is exactly the base bias amplifier. So what do we do? First thing we do is in this AC analysis that we short circuit all capacitor and the DC sources. So DC sources is short circuited, becomes ground. Capacitor over here, it becomes a short circuit, therefore becomes just a conductor. So the circuit now become this equivalent circuit over here, right? It becomes this equivalent circuit over here, where we see that between V input and the base, we just have RB, but between the V input and RB, it becomes just a connected wire. That's why we have V in and then connected to RB directly without any capacitor. And then with RB, RB then is connected to the base. So connected to the base, and then we have, therefore, we start over here the model of the BJT that we've seen just now. So this is a in pi model. So we have a resistor representing the base resistor. We have V pi, and then we have IC, the current that is through the collector circuit, and then of course RC IC is connected to RC, and then RC connected to DC. We short circuit, become ground, so it becomes ground, and then this collector is also connected to load resistor. So we have over here the load resistor. So this is the model when we do AC analysis. So this is the AC analysis equivalent model using the pi model of the transistor of this circuit, amplifier circuit. Now that we have done this, we can basically identify the input and output impedance of our amplifier. So what is the input and output impedance? Input impedance is this one over here, Z input. So this part on the left hand side is the input, on the right hand side is the output. Input impedance is the impedance of this whole part view from this point of view. So we have basically two resistors, RB and R pi. So RB in parallel with R pi is the impedance input, right? And then in output impedance, of course, we are going to separate the RL because RL is the load, is not part of the amplifier. So impedance output is only RC in this method. And then of course, again, we recall that IC, what is IC? IC is proportional to V pi with a certain coefficient of GM. So from there, we can calculate the voltage gain. So we can see here from the pi model, we can write Ohm law as we mentioned just now. V input, because voltage gain is basically, I'm going to skip directly here. Voltage gain is AV equals to V out over V in, right? So we have to find what V out is, what V in is. So we back over here, up here, V in is, as we mentioned, is IB multiplied by beta R prime E, right? So that is V in. So right, so V in is the voltage input of the amplifier over here, which is also V pi. So it is IB, the current that goes through the base, IB multiplied by V pi. So V pi, we mentioned just now, V pi is also equivalent to beta R prime E. So it depends on what parameters is given to you. Probably if it's not, if V pi is given, then it's easy. It's just IB multiplied by V pi. Otherwise, is IB multiplied by beta multiplied by R prime E, and R prime E, of course, we have seen the calculation just now. So usually, if we need any formula like this, then it will be provided in your exam. So, but you just have to know that V input is the voltage over here, V input, And then in collector circuit, we are going to find V output. So what is V output? V output, of course, is the current IC multiplied by the resistor that we have in the output. And we can see that in the output, the resistor that we have, there are two. There are RC and RL, so they are in parallel. So IC multiplied by RC and RL, and we know that IC is beta IB, right? IC is beta IB, or if we given with this parameter GM and V pi, then IC is also GM V pi. So therefore you got over here V out, and then of course the gain of the amplification, the voltage gain, is just the ratio of 2 V output divided by V input. So this is what we get over here. Depending on which parameter is given, it might vary, but here over here it shows a very simplified equation or expression that explain exactly what happened in this particular amplifier circuit. So it's not going to be always this. You have to just apply V out over V in. You have to identify and look at the formula that is provided to you. So for example, in this case, it's going to be RC in parallel with RL divided by R prime E. So R prime E is the resistor equivalent in the T model just now. So it's not given in this particular schematic diagram over here. So that is more or less on what we have in calculating voltage gain. So we have seen just now the model, equivalent model of an amplifier of amplification using BJT in small signal and low frequency. But what we define as low frequency, I haven't mentioned just now. So what we define as low frequency is usually the frequency that is less than 100 kilohertz. So we have, if you have a signal to amplify that is less than 100 kilohertz, then to analyze it, we can use the model that we have used just now. But for example, if you are treating a signal that is larger than 100 kilohertz, operating at higher, what we call as higher frequency, larger than 100 kilohertz. So this is not a signal in power electronics. It's more a signal for electronics, a purely electronics circuit. So in a frequency where you have the V input, here is noted as Vs, the voltage input to amplify larger than 100 kilohertz. What happens is basically the internal capacitance of the transistor. If you look at your transistor, the internal capacitance of it will have an effect, and it will affect the performance of your amplifier. So we need to include the capacitance of the transistor. So this is what going to happen. So we have a model, a not low frequency pi model. So in here, what we are going to show you is a high frequency hybrid pi model. So it's high frequency model. So in high frequency model, what do we have is so if we look at the low frequency model first, as we have just now, here of course the model, we still have the capacitor, coupling capacitor C1 and C2, because probably it is not mentioned, it is for AC analysis, because if it was for AC analysis just now, we can eliminate the capacitor, simplify it. But if it is for DC analysis, then the capacitor could still probably there, but in general it is there. It's just depending on the analysis. So nonetheless, back to our discussion just now. So this is the low frequency model that we have discussed. So we have all the resistor. If you have a resistor before the base current, then this is the resistor after the power supply, and then we have the RB resistor at the base, and then the equivalent resistor for the BJT R pi, and then we have and R0. So R0 is a resistor that related to the BJT as well. Usually it can be neglected, but it depends on what is mentioned. Because it depends on the frequency. And then we have RC, the collector resistor, and the load, right? So this is the normal model as we have seen just now. When you have a high frequency, you will see that there are some addition, especially in terms of capacitor. So where are the capacitor? So we have one over here. So the R pi and V pi is still over here, but we need to add this capacitor. So there is C pi and C omega 1. So C pi and C omega 1 will be depending, it will be given or will be depending on the transistor. So these are the two capacitor that is attached to the base of the BJT. And then we have another two CCE capacitor of the collector part, and then C omega C omega output, which will be depending on the frequency. So the difference is only that you have to integrate these four capacitor, two on the base and two on the output side, which is on the collector, on the emitter side. Okay, so that's the only part. And then of course, once we have that, just now as we have discussed, we only have impedance, equivalent impedance, input and output, but now we are also going to have the input capacitance equivalent and input output capacitance equivalent. Okay, so another thing that we need to precise is that there is a cutoff frequency in which the amplifier will work properly. Beyond those frequency, it will not work properly. So there is two cutoff frequency that is related to the input FHI, and one is related to the output FHO. So you can calculate basically the what we call as cutoff frequency below with the amplifier should work properly. So it has a formula, so it needs your RS, your Z and C input. Here is gonna need the ZO and CO of the output. And then of course, as we were discussing about the high frequency equivalent model, about the cutoff frequency, the thing that I have not mentioned, so we need to integrate it for the low frequency model as well. In low frequency model, there are also cutoff frequency, right? When the model assumes small signal at relatively low frequency, there is a limit of frequency as well in which the model is valid. So there are two cutoff frequency for input. I'm going to call it as here as FL in, output impedance FL out. So it's related to both of them. So if we have the equivalent model like this for the low frequency, as we discussed just now, then we would have this formula for the input and output cutoff frequency. So it needs the value of your coupling capacitor C1 and C2, and it needs the value of your input impedance and output impedance ZI and ZO. So ZI is, as we discussed just now, is RB parallel R pi, and ZO is basically just RC over here. So that's all our discussion on BJT and its application, which is mostly the simple amplifier. And we have today look at the tools that is available that we can use to basically analyze those amplifier. So the first one is basically to model the transistor, the BJT, using either T or pi model. The pi model is the more frequently used. And then after having model the transistor, we have looked at the equivalent model for the amplifier, and we have discussed a bit about the AC part of the analysis of the equivalent model of the amplifier. So that's all on BJT. Next week we are going to discuss about MOSFET, and in MOSFET we are going to look directly, because MOSFET is also we could say as a kind of transistor, but it's not a transistor. It doesn't have the same operating principle of base current, and it is not a current control device, but nonetheless is more or less the same thing with same characteristic curve that we are going to look at. So next week we're going to discuss very briefly on the operating principle of MOSFET, and then directly jump into another application which is also interesting, and the application is basically digital, what we call as digital switching. Okay, so thank you very much until we see again in next week for discussion about MOSFET.